All right, this is the next set of problems. I believe this is page 3 of our part 2 review. And we're going to treat this again as no calculator. So let f be the function given by this f of x. Find the domain of f and justify your answer. So this is back to like a pre-calculus problem. F is a rational function. Its denominator can't equal 0. And because we have a square root in the denominator, we need to ensure that the expression under the square root stays positive. So for domain, we need to make sure that x squared plus x plus 1 remains greater than 0. So let's find the zeros for this. I'm going to use quadratic formula. And I'm suspecting that I'm going to get imaginary zeros. This is probably positive, but let's see. Negative 1 plus or minus the square root of 1 squared minus 4 times 1 times 1 all over 2a. So yeah, this is imaginary. That means that there are no real number zeros. And if I start plugging some numbers in for x, like say I plug in x equals 0, I get 1. If I plug in x equals negative 2, I get 4 minus 2 plus 1. That's positive. So x squared plus x plus 1 greater than 0 is positive for all real numbers. So that means that the domain of f is all real numbers, or negative infinity to infinity. I don't think it matters how you say that. There are no restrictions on this graph. For part B, it says in a negative 5 to 5, negative 3 to 3 viewing window, sketch the graph of f. So, all right, so let's set that up. So we're going from negative 5 to 5. So here's negative 5. Here's 5. Now, I don't think that means that we should just be plugging in these 4 endpoints of the window to see where we are. Let's kind of think about this here. So f of x is, excuse me, is rational in that it's a fraction. I guess it's not purely rational, but I want to think about like what's happening as we start plugging in endpoints. I can go ahead and find f of negative 5 and f of 5 and all of that. We can do that. That'd be negative 10 over square root of 25 minus 5 plus 1. Negative 10 over radical 21. Okay. And f of 5, I could do that. That's probably not going to be very productive either, right? That's going to be positive 10 over radical 31. Okay, well, that's not all that helpful. That tells me there's a point down here and a point up here. A y-intercept would be good. F of 0 equals 0 on top over 1, so 0. Okay, so there's a point I am willing to plot. Here you go. What's more important, I think, is to come up with the fact that there are probably horizontal asymptotes. I guess I don't need arrows on the end of this, so maybe I do want to kind of plot these values. So what is negative 10 over root 21? Let's see. Square root of 16 is 4. Square root of 25 is 5. So this is like roughly 10 over 4 point something. That's roughly 5 over 2. So I'm going to plot this at like negative 2.5-ish. Here, this is like 10 over something between 5 and 6, 5 point something. So that's roughly 2-ish. Okay. And let's see. Do they want me to do concavity and all of that? I'm not quite sure. I'm trying to think of like how accurate I need this graph to be. This is such an unusual question. This is a pretty old question. It's pretty unusual that we would have to graph something like this without being given this f prime information first. So I'm going to, let's see. I'm going to check my concavity. No, I don't want to do that. I don't want to find f double prime. I think I'm going to assume that this is one of these graphs. It probably approaches its asymptote here, and I bet it does one of these. You know, I'm not supposed to go beyond that, though, because I'm just in this viewing window. So I'm going to say it probably looks something like this. I could get more accurate by plugging in values for 1 and 2 and 3, and I just don't want to go through all of that. Okay, so I'm not too worried about being more accurate for that one. I don't know. Write an equation for each horizontal asymptote for the graph of f. Okay, so this is saying, well, there is some sort of value for the limit as x approaches infinity of this 2x over the square root of x squared plus x plus 1. We've talked about these infinite limits before. We've not talked about L'Hopital's method yet, which is what we could really use to get down to this, but just think about this. The x and the 1 are insignificant as we start plugging in large values. It's the x squared that takes over. So this is really like thinking about, well, what happens to the behavior of 2x compared to square root of x squared? We're talking end behavior, so we just go with leading coefficients. Well, that acts a lot like 2x over x, and that acts a lot like y equals 2. So there would be, as x approaches positive infinity, a horizontal asymptote at y equals 2. And then as x approaches negative infinity, the only thing that changes is that this 2x will become negative. But still, we will be looking at comparing the same values. But if we're putting in a negative for x, it's going to be 2 times a negative. So this will go to negative 2. So y equals negative 2. So those are the two horizontal asymptote equations. And that tracks because even though I got a number, did I get a number lower than 2? What did I say? This is like 5 over 2. Yeah, this is like 2.5, right? Remember, you can cross through horizontal asymptotes and come back to them. So this probably does one of those where it dips below and comes back. All right, take a look at part D. Find the range of f. Use f prime to justify your answer. Oh, so that connects to what I just said. The range of f, and I think that my answer key might be, is my answer key wrong about this? Let's see. The range of f is saying, I know for sure that ultimately it goes between negative 2 and 2, but does this graph dip below? Is there a relative minimum right here before it comes back? So let's check. Let's check for critical numbers. Are there any relative extrema on this graph? So x plus 2 over x squared plus x plus 1 to the 3 halves. Is that ever equal to 0? Well, yeah, if x equals negative 2. And is the denominator ever equal to 0? No, so it's never, this is never undefined. We already looked at that in the previous part. So let's do a little number line here. At negative 2, I wonder if there's a relative, minimum. I've really sketched this graph wrong then, haven't I? I should probably go back and plug in points. All right, so let's see, f prime. So let me plug in negative 3. Remember, we know that this is positive, so I don't have a ton of hard work to do here. If I plug in negative 3 into x plus 2, I get a negative. And if I plug in something to the right of negative 2, like 0, I'm going to get a positive. So yes, f does decrease and then increase at negative 2. So I really need to reevaluate the way I did this problem, because at negative 2, apparently it probably like dips down like this, does one of these. Okay, so what is the range? Well, we need to go ahead and find f of negative 2 because that is the lowest point. I know that every point after that, the graph is starting to approach the horizontal asymptotes. So back to f. F of 2 is 2x, f of negative 2, excuse me, is 2 times negative 2 over the square root of positive 4 minus 2 plus 1. That's negative 4 over radical 3. This is the absolute minimum. So the range is negative 4 over radical 3 up to positive 2. Do we hit positive 2? No. Yeah. My original answer key, I'm just realizing I did not have that done correctly. I should probably find some other points in here. I should probably plot all of these values, but I just don't want to make the video super long. So I could plot more accurately. I can't imagine they really want us plugging in all the x's between negative 5 and 5, but maybe they do. I don't. I don't know. All right, what's the next problem? Let's see. Number 16. This seems like a related rates problem that we've seen before or something like it. All right, so as shown in the figure, water is draining from a conical tank with a height of 12 feet and a diameter of 8 feet. So we have to be careful of that. The radius is 4 feet. So I kind of just want to cross that out. The radius is 4 feet. Into a cylindrical tank that has a base with an area of 400 pi square feet. That's the area of the circle on the bottom, which never changes. As the water fills, the area of the circle base stays the same. The depth h in feet of the water in the conical tank is changing at a rate of h minus 12 feet per minute. And let's see. And let's think about that. Do we need to make that negative? Because the conical tank is draining, but remember, its max height is 12, and then any height you plug in after that will be something less than 12. So h minus 12 will come out negative. So we do not have to put a negative sign in there. The volume of a cone is this. Okay. Write an expression for the volume of water in the conical tank as a function of h. That means that here's our volume as a function of r and h. We need to just get h's in the variable. So for the first part, I need to say, actually, let me do this down here. So there's a relationship in this cone between h and r. So h equals 12 feet when r equals 4 feet. Remember, we're not using the 8 feet. That means that h compared to r is 12 over 4. I could also say h is equal to 3r. I want to get rid of the r, though. So I don't want to solve this for h. I want to solve this for r. So h divided by 3 is equal to r. Because I want to take this original volume of a cone and replace the r with this expression. So 1/3, let's just make that pi over 3 times h over 3 squared times h. So now volume is just a function of h. So this is going to be pi. H will be to the third. We're going to have 3 times 9, so over 27. So this is my volume of the cone, just as a function of h. At what rate is the volume of the water in the conical tank changing when h equals 3? Indicate units of measure. All right, so I like to set up know, find, use. So what do I know in this problem? So I know that dh dt is equal to h minus 12. I like to put the labels on, feet per minute. They want me to find dv dt when h equals 3. And I'm going to use this volume formula that's only in terms of h that we just came up with. So v is equal to pi over 27 times h to the third. All right, so we're going to take the derivative with respect to t of both sides. That's going to make this 3 pi over 27, so pi over 9 h squared. And because that was a variable h and I'm differentiating with respect to t, I need a dh dt. After I've taken the derivative, I can sub in the numbers that I know. So I don't know dv dt at h equals 3, but I can plug in 3 here. 3 squared is 9. And remember, dh dt is h minus 12, but that'll be 3 minus 12. And I just need to calculate, right? So this is what? The 9's cancel. This is negative 9 pi. Include units in your answer. Yeah, so this is changing volume. So that's going to be cubic feet per minute. So the cone is draining at negative 9 pi cubic feet per minute. I think we did have the same problem back when we learned related rates. Okay, what about part C? Let y be the depth, excuse me, in feet of the water in this cylindrical tank. At what rate is y changing when h is 3? Indicate units of measure. So again, this is, let's see. So what do I know? What do I want to find? What can I use? Now we're talking about this big tank here. So what do I know about those rates? Because the rate that they're asking me to say, like, okay, y is the height of the water. Remember, we know this is 400 pi. So they're asking me to find the change dy dt. But what have they given me? Really, I have to use my answer from the previous part. Remember, I do actually know dv dt for this problem, because if the cone is draining at this rate, that's the amount of water, that's the rate at which water is entering the cylinder. So it's positive 9 pi cubic feet per minute. If we take it out of weird numbers with pi and stuff, if this is losing 10 gallons in a minute, it means this is going to gain 10 gallons in a minute, right? That's all we're saying. Okay, what do they want me to find? They want me to find dy dt when, was it h equal to 3 again? Yep, when h equals 3. Now, why is that important? Because I thought we were talking about y. Remember, this is dv dt at h equals 3. If they weren't asking me about when h equals 3, I'd have to go back and figure out a new dv dt. And then what am I going to use? So I'm not using the volume of the cone, I'm using the volume of the cylinder. A cylinder is just the area of its base, which they told me was 400 pi, times the height, which is y. So I'm going to take the derivative with respect to t of both sides. The derivative of y is just 1, so dy dt. And again, we know this is 9 pi. So we just divide. The pi's are going to cancel out, 9 over 400, and the label would be back to feet per minute, because we're just talking about the height of the cylinder. So that's a linear measurement per minute. All right, what's next? Let's see. Do I have time? I have time for maybe both of these. Let's find out. All right, this one. Suppose that the function f has a continuous second derivative for all x, and that f of 0 equals 2, f prime, oh wait, I don't think we can do all of this problem. Can we? Oh wait, maybe we can, sorry. Never mind, I thought it was going to start going into tailored. Okay, anyway, we have all this information. Let g be the function whose derivative is given by this for all x. Write an equation of the tangent line to the graph of f at the point where x equals 0. All right, what do I need for a tangent line? I need a point and a slope. The point is supposed to be when x equals 0, I need f of 0. And they've given me that. So the point is 0, 2. What's the slope? I need f prime of 0. They've given me that. F prime of 0 is negative 3. So that's easy. Y minus 2 equals negative 3 times x minus 0. Simplify that if you want. That's all I have to do for the first part. Part B. Is there sufficient information to determine whether or not the graph of f has a point of the inflection? That's weird. A point of inflection when x equals 0. Explain your answer. Do we have enough information to decide if, okay, so what do we need for a point of inflection? F has a point of inflection if f double prime of 0 has a point of inflection at 0, if f double prime 0 equals 0 or undefined, and f double prime of 0, f double prime of x changes signs at x equals 0. We do have this. We were given this, but we don't actually have the function. We don't have any information to show us that f double prime changes signs. So there is not sufficient information. to determine a POI at x equals 0 because there is no info about a sign change of f double prime. Okay, part C. Given that g of 0 is 4, write an equation for the line tangent to the graph of g at the point where x equals 0. So here's another tangent line equation. So we need a point, which they gave me, 0, 4, and we need a slope. Now this is going to take a little more work because I need g prime of 0, and they give me g, but they don't give me flat out g prime. So, oh no, they do give me g prime. Oh gosh, okay. So they give me g prime. All I have to do is, for this part, is plug 0 into that, right? So that's going to be, instead of scrolling up and down, I've got it right here. So that's going to be, let me do it this way. G prime of 0, okay, e to the 0 times 3f of 0 plus 2f prime of 0. E to the 0 is 1. 3 times f of 0 is 2. Plus 2 times f prime of 0 is negative 3. 6 minus 6 times 1, that seems like 0. All right, so what's our equation? It's just y equals 4. You could say y minus 4 equals 0 times x minus 0. That's still correct. All right, so far this hasn't been too bad. Let's see what part D is. Part D looks like it might be gross. Okay, show that g double prime equals this. Okay. And does g have a local max at 0? Justify your answer. So first, let's show that g double prime equals that. Okay, so g prime, I need to have it written down here. E to the negative x, no, see? E to the negative 2x times 3f of x plus 2f prime of x. Okay, we are taking the derivative of a product where this is the first function and this is the second function. So it's first times derivative of the second. The derivative of 3f of x is 3f prime of x. The derivative of 2f prime is 2f double prime. Plus second times derivative of the first. So the derivative of e to the u is e to the u times u prime. So there's a times negative 2 in there. All right. And I'm supposed to show that that's this. So I'm probably supposed to factor out, looks like they've factored this out, an e to the negative 2x. E to the negative 2x. If I factor that out, I have 3f prime of x plus 2f double prime of x. There's a minus 2 right here, so minus 2 times 3f of x plus 2f prime of x. And I have to get it all the way to this, so now I need to distribute and combine some like terms. 3f prime of x plus 2f double prime of x minus 6f of x minus 4f prime of x. And let me get it in the same order they have it. So they have that there should be a negative 6f of x, which I have. And then it's f primes next. So 3f prime minus 4f prime is minus f prime of x. That's a good sign. And they end with plus 2f double prime of x. Okay. Show that that's true. Done. Does g have a local maximum at 0? Now, you could put numbers in on either side thinking about first derivative test, except we don't have any information about g. Like, we don't know if it would be positive or negative on either side if we're plugging in like something to the left of 0 and something to the right. So this is the second derivative test that we're trying to use. So what is g prime of 0? Because, let's see, g prime of 0, where's g prime? Did we find that earlier? Sorry, g prime of 0, yeah, g prime of 0 equals 0. We know that. We found that earlier. That means that x equals 0 is a critical number. There's a horizontal tangent there. And then the question for the second derivative test is saying, well, what is g double prime of that number? Is it positive or negative? So let's plug that in. It's e to the 0 times negative 6 f of 0 minus f prime of 0 plus 2f double prime of 0. E to the 0 is 1. F of 0 was 2 minus f prime of 0 was negative 3 minus negative 3. F double prime of 0 was 0. So this is negative 12 plus 3 plus 0. So negative 9. So there is a horizontal tangent. There's a critical number at x equals 0. And the graph is concave down at x equals 0. So what does that mean? It means that this critical number where we have a horizontal tangent is a relative max. What's my justification for that? I'm going to say G has a local max because G prime of 0 equals 0 and G double prime of 0 was less than 0. You don't have to go into the full explanation. This is all you need. All right, I have time for that last question, so let's see. Because this looks nice and short. It's not a full out. This is not a full out free response question. I love these little things. Okay, so copy this. This is like a little puzzle we get to do at the end here. So down to the bottom of my page. Oh my goodness. All right. H of x is this fun function. Find h prime of 3. Now, h prime of 3 needs quotient rule. That's what they're testing you on. H prime of x needs quotient rule, I mean. So it's low, d high. The derivative of f of 2x is 2f prime of 2x. Minus high, d low, 3 times g prime of x. All over low, the 3 is included in there too. 3 times g of x will get squared. H prime of 3. I'm just going to show myself that I'm putting 3 into all these. Actually, I'm going to do a little bit of math. 3 times 2 is 6 times g of 3 times f prime of not 3, 2 times 3. Minus 3. F of, if I put 3 in there, I get 6 times g prime of 3 over 3 times g of 3, whatever that is, we will square it. Okay, now we're going to put numbers in. So 6 times g of 3 is 5. F prime of 6. Oh, wait, why do I have 6 and not... What have I done that's going wrong here? Let's see. Oh, I have that my answer is... I wonder if I'm missing a line here. I have that my answer is like still in terms of f prime of 6. Yeah. Okay. Anyway, so I'll fix that on my key too. So I don't know where this original problem came from. Otherwise, I would go try to find it. Okay. So anyway, let's do that then, because we don't have the 6 information. So 6 times 5 times f prime of 6. Okay. Minus 3 times f of 6. G prime of 3 is 2 over 3 times g of 3 squared. So all I can do with this is make it 30 f prime of 6 minus 6 f of 6 all over 15 squared. What's that, 225? That's as far as I can take that. I bet I accidentally cut a line off of the table. So yeah. All right, that's where this video finishes. If you have done all of this review so far and you're kind of understanding what's going on, maybe if you needed my videos to get through it, maybe run through it a second time then. You should be in really good shape for our first semester exam and also in a good spot for the AP exam.